discussed about the chemical equilibrium. Then today we have to solve the problems based upon the chemical equilibrium in Kp and Kc determinations. First problem is in the following system at equilibrium, comma G plus 3H2G equilibrium with 2NH3 equilibrium with 2NH3G. The reaction mixture contains the reaction mixture contains 0.005 mole nitrogen, 0.012 mole hydrogen and 0.002 mole ammonia. In a 2-liter vessel, in a 2-liter vessel, calculate Kc. See, the equilibrium constant Kc for the synthesis of ammonia is given by equilibrium constant Kc for the synthesis of ammonia is given as Kc is equal to NH3 molar concentration whole square divided by N2 into H2 to the power of 3, where NH3 is the mole, where NH3 is equal to molar concentration of ammonia that is in moles per liter. Therefore, molar concentration is given by concentration of ammonia, that is the amount of ammonia 0.0005 divided by 2 liters, that is moles per liter, that is in terms of moles per liter. 0.005 moles divided by 2 liters, that is equal to 0.0025 moles per liter, 0.0025 moles per liter. And concentration of nitrogen is given by concentration of this is 0.002 mole ammonia, 0.002 mole ammonia. This is 0.001 mole of moles per liter. 0.002 ammonia, 0.002 divided by 2 moles per liter is equal to 0.001 moles per liter. Whereas the concentration of nitrogen is given by molar concentration, active mass 0.05 divided by 2, that is in terms of moles per liter, that is equal to 0.0025 moles per liter. Molar concentration of hydrogen is equal to, what about the hydrogen? That is 0.012 moles divided by 2 liters. This is in terms of moles, this is liter. This is equal to 0.06 moles per liter. Now substitute the values. 0. Kc is given by ammonia concentration 0.001 whole square divided by nitrogen 0.0025 into hydrogen 0.006 whole cube. By simplification of all this, you can use the calculators. It is finally it is reduced to 1.852 into 10 to the power of 3. 1.852 into 10 to the power of 3. 10 to the power of 3. 10 to the power of 3. This is 1 into 10 to the power of minus 3 whole square. That is 2.5 into 10 to the power of minus 3. 6 into 10 to the power of minus 3 to the power of 3. By further simplification, it seems to be 1.852 into 10 to the power of 3. 1 mole of nitrogen, and 3 moles of hydrogen. Are mixed in a closed vessel of 1 cubic decimeter capacity. At equilibrium, if the vessel contains a total of 2.4 moles. Calculate the equilibrium constant Kc. Calculate the equilibrium constant. Kc for N2 plus 3H2 equilibrium with 2NH3. Solution. Here is N2, 3H2 and 2NH3. Initial number of moles. As I mentioned in the problem, 1 mole of nitrogen and 3 mole of hydrogen. 1 mole of nitrogen and 3 moles of hydrogen. Initially the amount of ammonia is equal to 0 mole. Number of moles reacted at equilibrium. Number of moles reacted at equilibrium. Assume the x moles of the nitrogen, because the degree of dissociation is x moles, and 3x moles of the hydrogen, then it gives rise to 2x moles of ammonia. Number of moles present at equilibrium. Number of moles present at equilibrium. Present at equilibrium. See the initial number of moles of nitrogen 1 mole, and number of moles of nitrogen that reacted at equilibrium position is x. Therefore, the number of moles of nitrogen that left under equilibrium condition is 1 minus x moles. 1 minus x. Initially, the number of hydrogen present is 3 moles. Under equilibrium condition, 3x moles of the hydrogen that would be reacted. Therefore, the amount of hydrogen left under equilibrium is given by 3 minus 3x moles. 3 minus 3x moles. Initial amount of the ammonia at 0th minute is 0 moles, and amount of ammonia formed under equilibrium condition is 2x. Therefore, the amount left under equilibrium condition is 0 plus 2x. Because across product side plus sign, across the reactant side minus sign. Therefore, the total number of the moles, that is 1 minus x moles of the nitrogen, 3 minus 3x moles of the hydrogen, and 0 plus 2x moles of the ammonia are formed under equilibrium. The total number of moles that present under equilibrium, the total number of moles present under equilibrium, the total number of moles present under equilibrium the total number of moles present under equilibrium 1 minus x moles of nitrogen plus 3 minus 3x moles of hydrogen plus 0 plus 2x moles of ammonia, that is equal to 1 plus 3 4, that is equal to 4 minus x minus 3x minus 4x minus 4x plus 2x, that is minus 2x, that is equal to 4 minus 2x moles. 4 minus 2x moles. Given 4 minus 2x moles is equal to 2.4. Given 4 minus 2x moles, that is equal to 2.4. Calculate the value of the x. Calculate the value of the x. That is 4 minus 2x minus 2.4 is equal to 0. Therefore, 4 minus 2.4 is 1.6 minus 2x is equal to 0, or 2x is equal to 1.6, or x is equal to 0.8 moles. X is equal to 0.8 moles. Since the volume of vessel is 1 liter, Volume of the vessel is 1 liter. Amount of nitrogen is equal to 1 minus x by 1 is equal to 1 minus 0.8 by 1 is equal to 0.2 moles per liter. 0.2 moles per liter. Amount of hydrogen is equal to 3 minus 3x by 1, that is equal to 3 minus 3 into 0.8 by 1, that is equal to 3 minus 2.4, that is equal to 0.6 moles per liter. 0.6 moles per liter. 0.6 moles per liter. The amount of ammonia formed under equilibrium. Amount of ammonia formed under equilibrium in molar concentration 2x by 1, that is equal to 2 into 0.8 by 1, that is equal to 1.6 moles per liter. 1.6 moles per liter. There is a Kc for ammonia is given by Kc for ammonia is given by concentration of ammonia whole square divided by concentration of nitrogen into concentration of hydrogen whole cube, that is equal to 1.6 whole square divided by 0.2 into 0.6 whole cube, that is given by this is in terms of moles per liter whole square. This is moles per liter. This is moles per liter into 0.6 moles per liter whole cube. It is given by 59.26. By simplification, 59.26. This unit is, this is mole into mole cube, this is mole square, moles per liter whole square, here moles per liter to the power of 4, that is equal to moles per liter to the power minus 2, that is 59.26. This is the value of the Kc. This is the value of Kc. Solution. N2G plus 3H2G equilibrium with 2NH3G. 2NH3G. Initial number of moles. Two moles of nitrogen and 2 moles of hydrogen. 2 moles of nitrogen and 2 moles of hydrogen. 2 moles of nitrogen and 2 moles of hydrogen. Number of moles reacted under equilibrium. Number of moles reacted under equilibrium. Number of moles reacted under equilibrium. Say 1.5 moles of nitrogen left under equilibrium means 0.5 moles would react. 2.0 initial minus 1.5. At equilibrium, if the vessel contains 0.5 moles of nitrogen, 0.5 moles of nitrogen, that is equal to 0.5 moles of nitrogen. If this is 0.5 moles of nitrogen, then 3 times of it hydrogen is, that is 1.5 moles of the hydrogen would react. 1.5 moles of the hydrogen would react. At equilibrium, amount of ammonia is not at all found. Number of moles present at equilibrium. Number of moles present at equilibrium. Present at equilibrium. Number of moles present at equilibrium. That is 2 minus 1.5, that is 1.5 moles. Initially 2 moles is present, 0.5 mole react, 1.5 mole left. Initially 2 moles present, 1.5 mole react, that is 0.5 moles present. What about the amount of the ammonia formed? What about the amount of the ammonia formed? See, 1 mole plus 3 mole, that gives raised to 2 mole, means the half of this value. Half of this value. 1.5 moles plus 0.5 moles 2, half of this, that is equal to 1 mole. Half of this is equal to 1 mole. How do you calculate? N2 plus 3H2, that is equal to 4 moles. 4 moles. That is a 2NH3, that is equal to half of this value. Half of this value, that is a half of the 4, that is equal to 2. Therefore 0.5 plus 0.5, that is equal to 2. Half of this 2 is equal to 1 mole. Half of this 2 is equal to 1 mole. Therefore the number of moles of the reactant under equilibrium condition, number of moles of reactants under equilibrium condition, number of moles, total number of moles under equilibrium, total number of moles under equilibrium, it is equal to 1.5 moles plus 0.5 moles plus 1.0 moles. 1.5 plus 2, that is equal to total 3.0 moles. That is 3.0 moles. Mention the relation between Kp and Kc. Mention the relationship between Kp and Kc. Kp is equal to Kc into RT to the power of delta n. RT to the power of delta n. Delta n is equal to number of moles of gaseous product minus number of moles of gaseous reactants. Number of moles of gaseous products is 2. Number of moles of gaseous reactant is 1 plus 3 moles. That is given by 2 minus 4. That is equal to minus 2. Delta n is equal to minus 2. Therefore, Kp is equal to Kc into RT to the power of minus 2. RT to the power of minus 2. Now tell me whether this RT to the power of minus 2 is less than 1, means this is a fraction, therefore Kc value is smaller, Kp value is larger, therefore Kp greater than Kc. Kp greater than Kc. So that is only the relationship Kp and Kc. As in PCl5 that dissociates to give our gaseous system PCl3 plus Cl2. Here number of delta n is given by number of moles of gaseous products minus number of moles of gaseous reactants. Products, that is equal to 2 moles. Reactant, that is equal to 1 mole. That is equal to 1 mole. Therefore, delta n is equal to 1. Delta n is equal to 1. Kp is equal to Kc into RT to the power of 1. RT to the power of 1. Kp is equal to Kc into RT to the power of 1. This Kpl is large. And also we discussed that in 2Hi gives rise to H2 plus I2. Here delta N is equal to number of moles of gaseous products minus number of moles of gaseous reactants. That is equal to 2 moles minus 2 moles. That is equal to 0. For Kp is equal to Kc into RT to the power of delta N. Therefore, Kp is equal to Kc into RT to the power of 0. Since RT to the power of 0 is equal to 1, therefore Kp is equal to Kc. Kp is equal to Kc. Okay, dear students, these are the problems that based upon the Kp and Kc values.